We're now going to take a look at a case study that will compare and contrast the fork join pool's way of doing things with other concurrency models that exist in the context of modern Java or very modern Java. And so I call this the FileCount Case Study, and we'll give an overview here to get everybody on the right wavelength, and then I'll cover some examples and we'll walk through the code. So this is going to evaluate different ways of doing parallel programming in practice. We're going to use the fork join pool and parallel streams and some other stuff in order to do the processing. So this is going to take those different models, and we're going to apply them on a common data set, and we're going to benchmark the results to determine trade-offs between conciseness and performance. And sometimes, as you'll see, there's a trade-off. Sometimes there's not a trade-off. That's one of the cool things about these abstractions. Sometimes you get the best of both worlds. You get very simple programming, and you get high performance. Sometimes there's a bit of a trade-off, but it's not a humongous trade-off. So let's take a look at the main program. This is the main class. This is the one that's the entry point into everything else. And what it does is it shows off the fork join framework as well as sequential and parallel streams. And we're going to use sequential streams in conjunction with the fork join framework for one of the models to evaluate, which, by the way, is what you'll be doing for programming assignment number 2. So programming assignment number 2 will have you do this. It'll have you encapsulate the programming and the control flow of fork join tasks using Java sequential streams. So it's a good way to ease into sequential streams by building on what we covered in assignment 1. The actual test program here and all the different classes it uses counts all the files in a recursive folder hierarchy and calculates the cumulative sizes of said files, the number of bytes that they contain. There's a couple of classes that you'll need to become familiar with to understand this. The first one is the AbstractFileCounter, as is the convention in Java. When it says abstract, that means that it just defines a bunch of obligations that subclasses have to extend and customize. So it provides foundational functionality for subclasses that compute the size of files and folders using different concurrency and parallelism techniques. And here are the fields and the methods that are in this class. The fields are used to keep track of things like the counts of the folders and the counts of the files and a given file. And then we have some methods that are going to be used to do various things. This is essentially an abstraction layer that offers common methods and fields that are shared by the various implementations of this particular abstract class. So the AbstractFileCounter is basically the base of this stuff, and then we subclass it and fill in the blanks. And I found this funny little meme that isn't always true, but sometimes it's worth remembering that adding another layer of abstraction does not solve every problem in computer science. We have this joke that says most problems in computer science can be solved if you add enough levels of abstraction. But not always. But in this particular case, it's a very useful abstraction layer. The FileCounter fork join task class is a subclass of AbstractFileCounter that applies the Java fork join framework and just good old Java 7 features. In other words, none of the streams, none of the cool, funky, newer functional programming stuff to compute the size of a folder and all the files that are reachable from that folder. It's best used for recursive tasks that can be split into smaller subtasks, basically divide and conquer algorithms. And this is reasonably good for divide and conquer. We'll see that there's better divide and conquer stuff, but this is sort of along those lines. The FileCounter sequential stream task subclass applies the Java fork join framework and Java sequential streams to compute the size of a folder and all the reachable files. And it's best used when we want the simplicity of streams to control the flow in the implementations of the various methods, in this case the compute method, while using the fork join framework to actually do the parallel computing. So it's kind of a neat hybrid approach that combines the simplicity of streams with the scalability of the fork join framework. And then the third and final approach is the FileCounter parallel stream implementation, which, as you might guess, applies Java parallel streams to compute the size of a folder and all the files that are reachable from that folder. And this approach is best used when we want data level parallelism, working with collections, and we want to abstract away from all the low level details of threading and forking and joining and all that kind of gobbledygook. So this is the approach that is arguably the simplest to program And then the question will be, is it still as efficient as one of the other ones? And we'll see when we do the benchmarking. So that's the end of the case study. Now, I want to tell you something kind of interesting. I originally started out this presentation by having the code that implemented all the stuff that we just summarized. And I was like, I really need to make some slides because it's not really very helpful just to look at code sometimes. Code is great. Code is ground truth. Code is like steel in Conan the Barbarian. There's a great scene in the movie Conan the Barbarian, which is one of Arnold Schwarzenegger's first kind of breakthrough movies. And James Earl Jones, I take it back, it's Conan's father, but it stars James Earl Jones. But Conan's father says to Conan, you can't trust men nor women nor beasts, but steel you can trust. It sounds a lot better if you're watching the movie. But at any rate, code you can trust. Code is the ground truth. However, it's very easy to get lost in the code. When you just start looking at code, it helps to have a bigger picture view. So I took my code and I gave it to ChatGPT 4's advanced data analytics tool, where you can give it basically a file. I give it the file. I give it the project file for this. I give it an IntelliJ project. I said, please read this project and then generate slides that explain to me what the key concepts and the key classes and key roles and relationships are in this code. And boom, it produced the starting point for these slides. Didn't produce all the cool diagrams. I had to do that myself. But it was really cool because it was able to reverse engineer a higher level view of the structure of the software and then put it into a form that made it easier to present to you folks. So what a great example of using these modern generative AI tools to help raise the level of abstraction for teaching computer science courses.